Hello, all my wonderful people. Today we are looking at 2.2, which is all about polynomial functions of higher degree. We do have a warm-up for this, so in your notes on this warm-up problem, I'm going to give you some time to do it. It just says find the zeros of f of x algebraically. So you're going to do algebraically first by completing the square and then solving. And then it wants you to graph the function and use the zero function of your calculator to approximate the zeros. Remember, zeros just means x-intercepts, okay? So we're just finding the x-intercepts. What are the x-intercepts? So I want you to work on this warm-up first of all, and then come back and let's check your work, and then we'll get started on today's lesson. Okay, so the first thing is that we have to set my equation equal to 0, right? So 0, and I'm going to do it on the other side. So 5x squared minus 10x minus 7 equals 0. And so we have to go through and remember the steps for completing the square. Those first two terms get put in parentheses. And I'm for sure going to run out of room, but write as small as you can, okay? And then I want this x squared to be, or I don't want a coefficient in front of the x squared, so I'm going to factor out of 5. Okay, so there we go. Excuse me. Now I need to find what number is going to go in the end of this trinomial, right? What number is going to go here to make it a perfect square? So that's where we do our b over 2 squared, where in this case my b is negative 2. So negative 2 over 2 squared gets me negative 1 squared, which is 1. So I can add 1 to the end of this. But if I add 1, I also have to subtract 1, right? Because I have to keep that equation balanced. Like that. Oh, boo! Just accidentally got rid of all of it. It's okay. Here's where we were. 2 parentheses, x squared minus 2x plus 1. Subtract 1. And then I still have the minus 7 equals 0 chilling. Okay. Now, x squared minus 2x plus 1 is factorable, so that factors into x minus 1 squared. Then I still have this negative 1 chilling, and I still have my minus 7 equals 0. If I distribute the 5, I get 5 times x minus 1 squared, and then 5 times negative 1 is negative 5, minus 7 equals 0. Okay, so in vertex form, I have 5 times x minus 1 squared minus 12. But I want to find the x-intercept, so I actually have to keep going, okay? So I'm going to set this equal to 0 again, so just to show you, I'm going to get rid of all of this because I am 100% going to run out of room here. Okay, so I'm going to set this equal to 0 again, and I'm just going to solve. So if we add 12 to the other side, and then I'm trying to solve for x, so I have to divide by 5. So 12 over 5 equals x minus 1 squared. And again, I'm trying to get that x by itself, so I have to take the square root of both sides, and the square root and the square cancel, so that's kind of the whole point. So I have the square root of 12 over 5, and I can't forget the plus or minus 2, and this equals x minus 1. Okay, now before I go on, something that's like super, super, super important is that I cannot have a fraction under a square root. So we have to do what we call rationalizing the denominator. So you got to think back all the way to our Algebra 2 skills, right? that the square root of 12 over 5 is the same thing as square root of 12 over square root of 5. But I can't have a radical on the bottom of a fraction. So I'm going to have to do rationalize the denominator. So what we do is we're going to multiply by 1, right? If I multiply this by 1, it doesn't change. But I'm going to multiply it by 1 in the form of root 5 over root 5. Okay, and the reason I did that is because that's what my denominator is. Okay, so I have square root of 12 times square root of 5, which is square root of 60, over square root of 5 times square root of 5 is square root of 25, right? Square root of 25, which is just 5. So this square root goes away, and that's the whole point, so that the square root goes away. So I've gotten rid of the square root on the bottom. However, now I still have to simplify the top if I can. So square root of 60, we can do 6 and 10. 6 is 2 and 3. 10 is 2 and 5. So here's my pair, right? So I can take one of those out, and then I have 2 times 5 on the inside, which is 15. So I have 2 root 15 on the top, 5 on the bottom. So hopefully that makes sense. How we got that. So root 12, wow, sorry, the square root of 12 over 5 is actually the square root of, is 2 root 15 over 5 equals x minus 1. And then lastly, I'm just going to add the 1 to the other side. So I get 1 plus or minus 2 root 15 over 5. Oops, that's a 2. I said 5 and I wrote 2. And I could keep going, but I don't necessarily need to. These are my 2 roots. Okay, those are my 2 zeros. And so then if I wanted to do it on a graphing calculator, you could just enter this in and then use the 0 function to find the same number. However, the number will be in decimal form, so you'll just have to plug this into your calculator to see what the decimal form of that is. Okay. Nice little warm up, huh? Feeling good? We have 2 objectives only today. Okay, so our first objective is to use the leading coefficient test. The leading coefficient test to determine end behavior of graphs of polynomial functions. What are the ends doing at the end of the function? And you'll see what I mean. And then we're going to find and use the zeros, aka the x-intercepts, of polynomial functions as sketching aids. So the first thing that we need to define is actually what is a polynomial function. Okay, so let's go here and let's look here at f of x, and this is a lot of stuff going on. Okay, so don't stress about it too much. Okay, right here, n is my exponent. My exponent cannot be negative. Okay, if my exponent is negative, it's not a polynomial function. So there's that. And then my a's, oh, and sorry, and it has to be an integer, meaning I can't have a fraction as an exponent. So my exponent has to be, I'm going to scroll down a little bit. There we go. My exponent has to be positive or 0, and it has to be an integer, meaning it cannot be a fraction or a decimal. Okay, and then all the numbers in front of the variable have to be real numbers. So you can't have an imaginary number there, okay? The highest degree, the highest exponent, whatever the highest exponent is the degree. And we're gonna talk about that a lot, okay? So the highest exponent is the degree. And then the number in front of the variable of the highest exponent is the leading coefficient. So again, we're going to talk about all of these in polynomial functions, and they all actually mean something and give us some clues on how to graph these polynomial functions. So for part A, or here it just says, are the following polynomial functions, identify the degree. So here I have an exponent of 2 and exponent of 4. Those are both positive and an integer. And then I have a coefficient of 7 and a coefficient of 9, which are both real numbers. So yes, this is a polynomial function. And the degree is the highest exponent. Well, in this case, the highest exponent is a 4, so the degree is 4. And it doesn't ask for it, but we're going to write the leading coefficient is the number in front of the variable of the highest degree, so that would be 9. And that's it, okay? Let's look at B. My exponents, I have 3, 2, so those are good. And then this one's a 1, but it's on the bottom of the fraction, and so I'm not really sure. So I'm going to write this, I'm going to bring this exponent up and write it on the top of the fraction. And when I do that, I get 2 times x to the negative 1. So when I'm bringing this up to the top of the fraction, it becomes negative. And since this is a negative exponent, and I'm not allowed to have negative exponents, that's what tells me that this is not a polynomial function. And then for C, I have x to the 1/3. This is not an integer. 1/3 is not an integer, right? Cannot have fractions or decimals. So this is also not a polynomial function. Okay, so hopefully we feel good about that. Let's move on and see what can I do with this information. Okay, so the next section is how can I recognize graphs of polynomial functions? Okay, so a couple things that we need to know is graphs of polynomial functions are smooth and continuous, meaning you're not going to get like a pointed edge like absolute value, right? There's the graph of absolute value. And see how it's pointed? That is not a polynomial function, okay? So all the corners are going to be smooth and rounded. There's also not going to be any gaps, so it's not going to go like this and then like that, right? That is not smooth and continuous. I can't draw it without picking up my pencil. So that is not a polynomial function. So you have to be able to draw it continuously, and it has all the corners and everything have to be smooth and rounded. So here, like an example of smooth and continuous functions, you could have something like this, right? That's smooth and continuous. The corners or the turns are rounded. You could have like negative x cubed, kind of, okay, smooth and continuous. Something that's not smooth, I guess I could just draw what I just have, right? A piecewise function is not continuous, or like a pointed graph like that, that is not smooth because it has sharp corners. So hopefully that makes sense. We're going to talk about the leading coefficient and the degree, because depending on the leading coefficient and the degree, we can do a general sketch of the graph, which is pretty cool, okay? So this is the one thing I want to note real quick. Remember when we talked about even and odd degrees? Even and odd functions, right? If it was even, it was symmetrical on the y-axis, and if it was odd, it had rotational symmetry. That is not the same thing as degree. It has nothing to do with degree. So don't even worry about that, okay? Degree is different than just whether or not a function is even and odd. So the leading coefficient test. Okay, so this is, we have 4 examples here that we're going to draw. And we're only talking about end behavior here. And I'll show you what we mean by that, okay? If I have an odd degree, so if the degree is 1 or 3 or 5 or 7, right? I think we get it. So like y equals, for an odd degree, if the leading coefficient is positive, so an example would be like 2x to the third, something like that. Okay, it could be 100x to the 11th, right? It doesn't matter. As long as this number, the leading coefficient is positive and the degree is odd. Okay, those are the only two things I care about. If I have a function with that, the graph falls to the left and rises to the right. I have no clue what's happening on the inside. It doesn't matter. It could turn 12 times. It could turn no times. It could turn once. It doesn't, well, I guess it would have to turn twice, right? But it doesn't matter what's going on the inside. Every single time, it's going to fall to the left and rise to the right. So I like to think of this x cubed, right? We know what x cubed looks like. It looks like this. There's x cubed. So the end behavior, if I take out the middle, the end behavior is doing that. It's falling to the left and rising to the right. If I have an even degree, so, you know, to the 4th, to the 6th, whatever, and it's positive, so y is equal to 3 times x to the 4th or something, as long as this number is positive, right, the leading coefficient is positive, the exponent is even, the graph is going to rise to the left and to the right. And again, I have no clue what's happening in the middle, and it doesn't matter for this case. The end behavior is always going to do this. So again, it says think of x squared, right? When we think of a parabola, it does this. Is a parabola an even degree? Yeah, right, because it's x squared. So we just think of what the end behavior there is doing. Okay, I'm gonna get rid of this and scroll down. There we go. Okay, if the leading coefficient is negative, but the degree is odd, so like y is equal to negative 2x to the third, I'm just gonna use the same example, but just negative, it just goes the opposite way. It's reflected over the x-axis. So it's rising to the left and falling on the right. And again, I have no clue what's happening in between. Doesn't matter. I just know that the ends are doing this every time. And with a negative leading coefficient on a positive degree, sorry, on an even degree, think of negative x squared, right? I have my parabola, but then it's flipped over the x-axis. So the ends are going down. And again, who knows what's going on in between. Okay, so what we're gonna do is we're gonna practice. It says use the leading coefficient test to determine the end behavior. Okay, so my highest degree here, so I'm gonna say my degree is 3, because it's the highest exponent, right? So it's odd. And the leading coefficient, and I'm gonna abbreviate it, is negative. It doesn't matter what the number is. All it matters is whether it's positive or negative. So since it's an odd degree that has a negative leading coefficient, it rises to the left and falls to the right. So we say rises to the left and falls to the right. Right, so on the left-hand side, it goes up, and on the right-hand side, it comes down. And that's it. Okay, for part B, my highest degree is a 4. So the degree is 4. which means it's an even degree. So it's either both going to go up or both going to go down. And then the leading coefficient is a positive 1, so it's positive, which tells me that my ends are going to go up on both the left and the right side. So we can say this rises to the left and right. Okay, we have 2 here for you to try. So go ahead and just follow what I did in examples A and B. And then when you're ready, hit play and check your work. Okay, so let's check your work here. For C, we have a degree of 5. My leading coefficient was positive, so this should fall to the left and rise to the right. And for D, my degree was 6. My leading coefficient was negative, right? Negative 6. So it falls to the left and to the right. So what this allows us to do is to just look at a function and be given the general shape of it, right? I know what the ends are doing. I don't know what's happening in between yet. We will. But for at least right now, I know what the ends are doing, okay? So now what we're going to do is we're going to look and we're going to get more specific points so that we can actually graph these functions that have a degree of 4 or a degree of 6 or whatnot, okay? So let's clear this out and go down. And we're going to talk about finding the zeros real quick. So the zero of a function is just the x-intercept. So we call them zeros now. So finding zeros, it says it's one of the most important parts in algebra, right? We did it when we were factoring. We did it in the quadratic formula. We do it by completing the square. Like there's so many different ways that we find the zeros. And so finding the x-intercepts is super, super important. And so we have a couple things that we're going to go over. And then we're just going to be practicing quite a bit, okay? So the first thing is that a function f has at most n real zeros, where n is the degree. So if I have a function that is a 4th degree, it cannot have any more than 4 x-intercepts. So if just, for example, the graph of x to the 4th, it cannot have any more than 4 x-intercepts. It can have less, right? It can have 0, 1, 2, or 3, or 4, but it cannot have any more than 4. So whatever the degree is, that's the highest, that's the most x-intercepts it can have. The number 2 says the graph has at most n minus 1 relative extrema, so maximums or minimums. What that means, I don't want to draw that part. So if I have a degree of 4, just to keep with the same example, it can't turn. So there's 1 turn, there's 2 turns, there's 3 turns, cannot have any more than 3 turns. So in this case, there's 1, 2, 3. Can it have less? Sure. Right, there's just 1. That works too, right? But a degree of 4 cannot have any more than 3 turning points. So that's kind of that first paragraph. Now let's look at this one, factoring. Hopefully we're feeling good about factoring. If not, please reach out. Make sure you get some help on factoring because you have to know how to factor. It's just a requirement, okay? So finding the zeros. So zeros are the values for which f of x is equal to 0. So really just all of these things, zeros, roots, factors, zeros, roots, and x-intercepts are kind of all the same thing here, okay? So zeros is just usually what we solve for. Same thing are roots, okay? Factors, now this is really important. So let's say that I have a 0 at x equals 2 and x equals negative 5. Just making stuff up, okay? Factors are expressions that are multiplied to form a polynomial. So factors, when I ask you what the factors are, this is when we write my x minus 2, because I always switch the sign, and x plus 5. Those are my factors. Okay, so even though these are the zeros, right? These are the x-intercepts. These are my factors. Okay, then we have to talk about multiplicity. So I'm going to do it actually over here on the left. Multiplicity determines the behavior of the function. So this is kind of crazy. Let's say that I have like a x minus 2, right? But then I have x plus 5 squared. But then I also have like x minus 7 cubed, right? All different factors there. So I just kind of briefly want to go over what happens at each one. So here, the multiplicity is just the exponent on the factor. So here the exponent is a 1, right? If the exponent is 1, I want to change these numbers to be smaller. Let me do that. Let me change these to be a little bit easier to work with. Let's call this a 3, and let's call this a 4. Okay, so 1, 2, 3, 4. 1, 2, 3. Okay, so this tells me that I have a 0 at positive 2. Okay, awesome, right? That's right here. Woohoo. This tells me I have a 0 at negative 3. And this tells me I have a 0 at 4. Now, what's really, really important is that we pay attention to what these tell us. If my multiplicity, so if this is just a 1, the graph just cuts straight through. Okay? If the multiplicity is a 2, or really, I should say, if it's a 1 or a 3, the graph goes through. It goes over the x-axis. So if it's an odd number, it goes over the x-axis. If it's an even number, 2, 4, 6, 8, right, then it bounces off. So I'm just going to draw end behavior. So at negative 3, because this has a multiplicity of 2, it's going to come down to negative 3 and bounce. Okay? And then it's going to come, and then at positive 2, it has a multiplicity of 1. So it just goes straight through. And then since this is still odd, it still goes through. But as the multiplicity increases, so as I get to a 3, it kind of curves through. And it does something like that. And that would be my graph. So that would be an example of a graph. So graphs tend to flatten out with multiplicities greater than 1. So as the multiplicity increases, the graph kind of flattens out a little bit. But really, we just need to know 1, 2, and 3. So at 1, it just cuts straight through. At 2, it bounces at a multiplicity of 2. And then at a multiplicity of 3, it curves through. So think of like x cubed, right? The graph of x cubed. Does that? That's exactly what it's doing. So let's look at some examples because I know that was a lot of information, right? So let's look at the first one. It says, in addition to what examples 3 and 4 ask you to do, give the multiplicity for each 0. Oops, excuse me. What did that happen? There we go. Give the multiplicity for each 0. State whether the graph crosses the x-axis or touches the x-axis and turns around at 0. Finally, at each 0, decide whether or not the curve flattens out. So we're just going to draw it and go with it, okay? So find all the real zeros of this, and we want the algebraic solution. Well, the first thing that I see is that I can factor out an x, right? I have an x cubed, an x squared, and an x. So I'm going to factor out an x. So when I take out an x, I'm left with x squared minus x minus 2. And because we paid really good attention in Algebra 2, we know that this is factorable, and this is x minus 2, x plus 1. So what I have now are my factors. I have a factor of x, I have a factor of x minus 2, and I have a factor of x minus 1. So this tells me that I have my x-intercepts at And I'm just going to set them all equal to 0 and solve. So if I set x equal to 0 and solve, I just get 0, right? And the multiplicity on this guy is just a 1, so I write m1. Here, my multiplicity again, there's nothing written, so it's a 1. So if I set my x minus 2 equal to 0 and solve, I get 2. So I have a 0 at 2, and again, my multiplicity is at 1. And then same thing for this last one. If I set x plus 1 equal to 0 and solve, I get x equals negative 1. And the multiplicity here is 1 because there is no exponent, right? If nothing's written, it's a 1. So because the multiplicity is 1 on all of these, I know that they just cut through. So all cut through. They're just going to go straight through at those points. Okay. The next thing is I got to look at the degree. So the degree here is 3, so it's odd. And then my leading coefficient is positive 1, so it's positive. So this tells me that my ends are doing this. And so because of that, I know what the ends are doing, and I know where there are x-intercepts. So I can draw my graph. 3, 2. Okay, so I know, I'm going to change colors so we can, I know that I have an x-intercept at 0. I know I have an x-intercept at positive 2, and I know that I have one at 1. Okay, now on the furthest left, I know that it's going down. So I know that's happening. And on the furthest right, I know it's going up. And then because the multiplicities are 1, it just cuts through, turns, cuts through, turns, cuts through. And there's my graph. Okay, so it doesn't have to be perfect. It just needs to have the intercepts and it needs to have the correct end of behavior. Okay, let's look at another one. Find all real zeros and any relative extrema of f of x equals negative 2x to the fourth plus 2x. Okay, so again, the first thing that I see is that I can factor out a negative 2x squared. So I'm going to do that. Negative 2x squared I can factor out. And that leaves me with x squared minus 1, which is factorable. So I have 2x squared times x minus 1, x plus 1. So then once it's factored all the way, it should be pretty quick to find my zeros. If I set this equal to 0 and solve, I just get 0. But the multiplicity on this is a 2 because my degree, right, or my exponent is 2. If I set this one equal to 0 and solve, I get 1, and that has a multiplicity of 1, right, because of the exponent out here. And then the last one, I get negative 1, also with a multiplicity of 1. Okay, so this just tells me right here that it's going to bounce. So it's going to bounce off 0, okay? So then I'm going to go graph it. 1, 2, 1, 2. And I know that I have a 0 at 0. I know that I have a 0 at 1. And I know I have a 0 at negative 1. Oh, and I haven't found my end behavior, right? My bad. Okay, so my degree is even because my highest degree is 4. And my leading coefficient is negative because of that negative 2. So I know that both ends are going down. So then when I go to graph this, I know that this end is coming down and this end is coming down. Okay, and then the question is, okay, at negative 1, my multiplicity is 1, so it just goes through. My next 0 is 0, so at 0, it bounces, so it's going to come here and bounce. And then at positive 1, the multiplicity is 1, so it's going to cut through again. Does it have to be perfect? Heck no. Okay. It's going to be just fine. And then the only other thing I want to do is find the relative extrema. So I'm just going to use the min and max function. In the calc menu, which we've done before, right? You just go second trace or second calc, and then you can find the minimum and the maximum. So again, excuse me, here's a relative minimum, and then I have two relative maximums, and if you actually graph on your graphing calculator, these are actually at the same height, so there's really only one maximum. Okay, but double check to make sure that you guys are doing it right. Your minimum should be 0, 0. Okay, and then your maximum, you have two of them, like I said, so negative 0.707, comma 0.5 is 1, and the other one is positive 0.707, comma 0.5. So if you're not getting those, make sure you reach out, and we can go over how to do that on your calculator. Last one on this page is find the function with the given zeros. So now I'm given the zeros, and I want to find the function. So what I have to do is I have to write these as factors. So I'm going to use x. So x, and then because this is a minus 1/2, I know it's going to be plus 1/2. Right? I'm just writing the factors like we practiced up above. Then I have x minus 3, and then x minus 3 again. And I don't like that there's a fraction here, so what I'm going to multiply this whole thing by 2, and that's okay, I can do that. So this gets me 2x plus 1, because the 2 times x is 2x, and then 2 times 1/2 is 1. And then because I paid really good attention in Algebra 2, I know that x minus 3 times x minus 3 is x squared minus 6x plus 9. Okay, now I have to distribute. So 2x times x squared, 2x cubed, 2x times negative 6x is negative 12x squared, 2x times 9 is 18x, 1 times x squared is x squared, 1 times negative 6x is negative 6x, and 1 times 9 is 9. So f of x equals, and I'm going to go through and combine like terms. So I have 2x cubed, and then minus 11x squared, plus 12x plus 9. So that is the polynomial function that has zeros, negative 1/2, 3, and 3. So I want you guys to try part B. So go ahead and hit pause on the video, and then when you're done, go ahead and just hit play again. Okay, so hopefully we set this up as such: x minus 2/3 times x plus 4 and x minus 4. I need those factors. Again, I don't like that there's a fraction, so I'm going to multiply this by 3, so that goes away. So now I have 3x minus 2. And then again, I paid attention in Algebra 2, so I know that this is x squared minus 16. Right, this one's a positive and a negative, so when you multiply it, those middle terms cancel. And then I'm going to distribute. So I have 3x cubed minus, oops, I need to just write 16. 3 times 16 is 48, so 48x minus 2x squared plus 32. And then if I combine my like terms and write this in the correct order, I have 3x cubed minus 2x squared minus 48x plus 32. Okay, hopefully we feel good there, all that fun stuff. We are basically on the last page, so we're getting close. This extra example here says find all real zeros of the polynomial function, and it says without factoring, right? Because I don't know how to factor something that's x to the fourth. So in this case, all you would do is you would graph this on your graphing calculator, and then use the zero function on your graphing calculator. So I'm just going to do like a really bad job of drawing this. So my apologies. But it's here, here, cuts through, bounces, and then cuts through. Something like that, okay? So then I just use the function or the zero feature on my calculator, and I get that x is equal to negative 1.5. And because it just cuts straight through, that's a multiplicity of 1. And then x is at negative 1, but since it bounces, that's a multiplicity of 2. And then also at positive 3, but because it just cuts through, the multiplicity is 1. And then if we add up our multiplicities, right, 1 plus 2 plus 1 is 4, and that is my degree. And that's not a coincidence. That will always be the case, okay? If you add up your multiplicities, they should equal your degree. Okay, the last thing we're going to look at is how do I graph like all of this, right? This is a lot, okay? So we have what we call the 5-step strategy here, okay? First thing that we do is we use the leading coefficient test. What does the end behavior look like? And then what does the end behavior look like, right? What is the degree? What is the leading coefficient? Then we can find the x-intercepts by setting the equation equal to 0 and solving. So different ways of solving here. We can factor. That's probably the most common one. We can use a graphing calculator. We can complete the square. Or we can use quadratic formula. Okay, but we're just going to find the x-intercepts however we have to do it. And then determine the multiplicities at each x-intercept. Then we're going to find the y-intercept by plugging in 0. And then we're going to use symmetry if applicable. Wow, applicable. Okay, it's really late. Let's just move on with that one, right? So is it an even function? Is it an odd function? And then find the maximum number of turning points as a check. So keep that list handy because I'm going to have to scroll away from it. But we're going to go through and we're going to like number them as we go just so we can keep track. So the first step in the 5-step strategy is to use the leading coefficient test. So here, my degree, it's a D, there we go, is 4. So it's even, right? The highest exponent is 4. And the leading coefficient is positive. So this tells me that both ends are going up, right? Because I'm thinking of like x squared. I know what x squared looks like, and that has a positive leading coefficient and an even degree, and it goes up. Okay, so I did that. Second step is to find the x-intercept. So I'm going to set the equation equal to 0. And solve. So I see that I can factor out an x to the third. And that leaves me 3x minus 4. Okay, so my x-intercepts are, if I set this equal to 0 and solve, I get 0. And the multiplicity there is 3. If I set this equal to 0 and solve, I get 4/3. And that multiplicity, right, the exponent up there is a 1. So the multiplicity is a 1. Right? And then 3 plus 1 is 4, and the degree is 4. So we're doing good. Then the next step is to find the y-intercept. I'm going to plug in 0. So I have 3 times 0 to the 4th minus 4 times 0 cubed. I just get 0. So my y-intercept is at 0, 0. The fourth step is it even, odd, or neither? And so remember, we have to think back to last time, not the degree, but is the function. So here I have an even exponent and then an odd exponent. So since there's a mixture, it's neither. And then the last step is to check the number of turns. So we're going to do that after we graph it, okay? So here's my graph. I know that there's a y-intercept at 0, 0, and an x-intercept, right? And then my other x-intercept is at 4/3, which is just over 1, so like here. I know the end behavior, it's going up to the left and up to the right. At 0, it has a multiplicity of 3, so that means it's flattening as it goes through. So it looks something like that. Doesn't just go straight through. And then at 4/3, it's a multiplicity of 1, so it just cuts straight through. And then we have to ask ourselves, how many times does this turn, right? Or what's the most it can turn? The degree is 4. The most number of turns I could have is 1 less than that, so 3. And here I only have 1 turn. So that's good. Cannot have more than 3. So if I had 4 turns here, we did something wrong. Okay, let's do another one together. And we're gonna try it again. Okay, so step 1, the degree here. My highest degree is a 3, so it's odd. And my leading coefficient is negative, because the number in front of the x cubed is negative 2. So that tells me that my graph is rising to the left and falling to the right. Okay, second step is to find the x-intercept. So I'm going to set this equation equal to 0. Negative 2x cubed plus 6x squared minus 9 over 2x. Okay, so I'm going to take out, just to make this a little bit easier for us, okay, I'm going to take out a negative 1/2 x. And so if I take that out, this becomes a positive 4x squared. This becomes a negative 12x. And this becomes a positive 9. And again, because I did algebra 2, I know that this is 2x minus 3. 2x minus 3. And remember that 2x minus 3 times 2x minus 3 is the same thing as 2x minus 3 squared. Okay? So this tells me that I have a 0 at, if I set this equal to 0 and solve, I get 0. And the multiplicity on it is 1, because the exponent is 1. And then here, if I set this equal to 0 and solve, I get 3 over 2. And the multiplicity there is 2, because the exponent's a 2. Okay. Third step is to find the y-intercept by plugging in 0. So I have negative 2 times 0 cubed plus 6 times 0 squared minus 9 over 2 times 0. So that tells me I have a y-intercept at 0, 0. So that's good. Step 4 is this function, even, odd, or neither. Well, I have odd degree or odd exponents. Then I have one even exponent, so this is neither, so symmetry is not going to help. And then the last step is, what is the maximum number of turns that we can have? And it's always 1 less than the degree. So the maximum turns I'm going to be able to have is 2. Okay, so again, I'm going to draw my graph. I have an x-intercept at 0 and an x-intercept at 3 over 2, which is 1.5. I know what my ends are doing, right? Here it's going up, here it's coming down. At 0, it just cuts through. And at 3/2, it has a multiplicity of 2, so it's bouncing. So something like that. So then the question is, how many turns do I have? And I have one here and one here. So I have 2 turns, which is okay. I just can't have more than 2. Okay. So hopefully we're making sense. We are going to get so much practice with graphing, you guys don't even know. Okay. Let's do our last problem here. Sorry, my dog is deciding to lay on my lap as I'm doing this. Okay. So the last problem, it says the graph of f of x equals x cubed plus 13x squared plus 10x minus 4, and it's shown in the standard viewing rectangle. Use the leading coefficient test to determine whether the graph shows the end behavior of the function. Okay, so the degree here is 3, right? So it's an odd degree. And the leading coefficient is positive. So this tells me that the function should be doing something like this. But when I look here, right, that definitely is not what it shows me. I'm missing something coming down here. So the graph actually like loops around and does something like that. Okay, so no, we can say no, it doesn't show the end behavior, right? Just in the standard viewing window, which goes from -10 to 10. If I made this bigger, right, and looked at maybe 100 to 100 or whatever, maybe it would show. But as of right now, I know that that graph is not showing me everything because I know what it's supposed to look like. So that's something to keep in mind if you're graphing these on your graphing calculator. Keep in mind that it might not be showing you the entire function, right? Use your leading coefficient test to determine what should it look like and then decide if it's showing you the whole thing. Okay, guys, that is it for 2-2. Not so painful. If you have any questions, make sure you reach out. And then we will do 2-3 next, and I'll see you later.